So we talked last day about spaghettification. We got to example 4. Example 4 says a black hole has a mass of 7.2 times 10 to the 31 kilograms. Suppose a spaceship is 9.6 times 10 to the ninth meters from the center of the black hole. What's the gravitational field strength at this location? What's my symbol, Gershon, for gravitational field strength? Not F. Which G? Big G or little g? Okay, what's the equation? Have you figured it out how you can get it from your formula sheet? What is little g? More specific, because this won't help us right now, because little m they didn't give me. They gave me big M, and I don't know FG. So how does that contain it? Here's what we said. FG, what's the equation for the force of gravity, the universal one on your formula sheet? Big G. You could say M1, M2, but I'm writing it big G, big M, little m over R squared. What happens to the little m's? Okay, this gives us our equation for little g. It's hidden in there. It's big G, big M over R squared. Big G, 6.67 times 10 to the negative 11. The mass of this black hole, big M, 7.2 times 10 to the 31. This is a radius because it does say from the center of the black hole, so it's going to be 9.6 times 10 to the ninth. Don't forget the squared. Does this have to be bigger than 9.8? Well, no, you could be so far away from the black hole that G is less than 9.8, but I have a feeling this one will be bigger than 9.8. And again, all of you want to practice typing these into your calculator. You want to get quicker typing in big G and masses and scientific notation. That alone can save you 5 or 10 minutes on the test, right? I have no idea what the answer is here. I think I made a typo. Yeah, I'm missing a 2. 6.67 times 10 to the negative 11, 7.2 times 10 to the 31, divided by 9.6 times 10 to the ninth squared. Gershon, what'd you get? Yep. Units. Right in the formula, and also meters per second squared, because force divided by mass also has to be A, because F equals what. But yeah, usually for gravitational fields, we refer to it as newtons per kilogram. About 5 Gs. All of you could kind of function there-ish, but even raising your arm would be very, very difficult. Keaton, you got that okay or not? You're looking befuddled. Okay. Is that right? Or did I make a mistake? I got confirmation? Okay. What's the escape velocity? Good question. Sophia, have you happened to memorize the escape velocity equation? I can't hear what you're saying. Have you? Yes, sir. You have? Okay, if you have, knock me out. We'll do that. If not, we would derive it by conservation of energy, by letting the right two things be zero. But you need to be able to do one or the other. I will be asking you an escape velocity question. In fact, I should have said I like this question. I like this question. Yeah. Which you can get from conservation of energy. We re-derived it last class. Okay. Hey. If you did the last one, I can't help noticing on my calculator right now, I have big G, big M, and R squared. I think, Sophia, if I just backspace and put a 2 times in front, in fact, really, I could have just put a 2 times afterwards, but put a 2 times there, delete the squared, square root answer button. That'll work. I get an escape velocity. Wow, almost worked out evenly. 1, 2, 3, 4, 5, 6. I get an no. Same. 1.00 times 10 to the sixth. Almost a million meters per second. Exactly. 1.00 times 10 to the sixth. meters per second. C. At what radius from the center of the black hole does the event horizon begin? How do we do this? So the event horizon, that is where the escape velocity equals the speed of light. So we're going to start out with Sophia's escape velocity equation, which was v equals the square root of 2 big G big M over r. But we're going to get the r by itself. And then once we get the r by itself, we'll let escape velocity equal the speed of light. We'll put in 3 times 10 to the 8th. How am I going to get the r by itself? Luke, where is the r right now on the... But what's it in... You know what? We're going to do that later. What's it inside of? How do I get rid of a square root? What's the opposite of square rooting? Yeah. First thing I'm going to do, Luke, you're correct. I'm going to square this, square this. When I square the left-hand side, I'm just going to get v squared. When I square a square root, the square root just vanishes, and I get just this. Now I'll say, Luke, hey, where is the r right now? On the... Bleh, what am I going to do with the r? Yeah, the r is going to end up here, and the v squared is going to end up there. There it is. It's going to be 2 big G, not mass of the Earth, mass of the black hole. Luke, I've scrolled down. What was the mass of the black hole? I missed the times 10 to the 31. All over. And what we're going to do is we're going to let v equal the speed of light, which is on your formula sheet. If you've forgotten it, it's going to be in the constant section. What's the speed of light? It's going to be in the constant section where you have big G. It's going to be right in that same chart, I'm sure. Yeah, it is there, yes? Did I not put it somewhere in that chart? Yeah. 3 times 10 to the 8th. Oh, don't forget that there's a squared on this. Two times 6.67 times 10 to the negative 11 times 7.2 times 10 to the 31 divided by, let me look for typos, 2, good, good, 3 times 10 to the 8th squared. This is how small this star had to be compressed before it vanished from our sight, before light was no longer to escape. This is where the event horizon begins. This is, Liam, if you get any closer to this black hole than this, you're never coming out. 100, is it 106,720? So 1.07 times 10 to the 5th. Meters. There's another fancy name for the event horizon. We'll talk about that in just a second. Example 5. Suppose for some unknown reason the sun began to collapse on itself, maintaining its mass actually, like you asked in our thought puzzle, but decreasing its radius, getting denser and denser and denser and denser. At what radius will it become a black hole? This is called the Schwarzschild radius, named after the physicist who first proposed this when he saw Einstein's general relativity equations. Well, you know what? This here is the same radius as where the event horizon starts. So again, we can start off with escape velocity and then let v equal c. Luke, did you just derive the equation for the radius of a black hole? Yes. Can you go look at the equation that you just derived? Or do you want to... Oh, is it on the previous page? Okay, let's rederive it. Sophia, what was escape velocity? You said you'd memorize this. You said it was the square root of what? We want to find the Schwarzschild radius, also happens to be where the event horizon starts. Luke, where is the r inside of a square root? How to get rid of us? Oh boy, Mr. Dueck. It's going to be boom, boom. That gives us v squared equals 2 big G big M over r. Declan, where is the r right now? On the... Bleh. So we're going to go boom, boom. And what are we going to let v equal? Speed of light. So it's going to be 2 big G. Oh, it's our sun. What's the mass of our sun? That should be on our formula sheet, I'm sure. It's 1.98, but I can't remember the 10 to the... all over 3 times 10 to the 8th squared. You know what? I got most of these numbers sitting on my calculator. I think all I need to do, because I got the 2 and the big G and even the 3 times 10 to the 8th, I just need to put the mass of the sun in for where the black hole was. I'm going to do that. 1.9, and I got to insert an 8, and then the exponent is to the 30th. This is also my way of saying, if you haven't figured out how to toggle between overwrite and insert on your calculator, worth learning. Saves you some time. You get a crazy small answer. We would have to compress the sun to, that's in meters, 3 kilometers. What's 3 kilometers? Probably about from here to the McDonald's. Compressing the massive sun into a radius. Oh, sorry, the diameter would be 6 kilometers, because this is a radius. So the sun would be 6 kilometers wide. In other words, you could walk through the sun in about 45 minutes to an hour if you were speed walking. This is the crazy density of black holes. Let's write this down first of all. 2,930 meters. For various reasons, a star the size of the sun doesn't have enough gravity on its own to do that. Black holes can start to form with stars that are either 10 or 100 times the size of the sun. I can't remember. I'd have to go look that up. Put your pencils down, look up. Black holes can get much larger. How big can black holes get, you ask? How big can black holes get, you ask? How big can black holes get, you ask? I am so glad you asked. Initially, Einstein was skeptical. Schwarzschild was the scientist who proved that they could exist. What if you took the Earth? Oh, here's the sun. Right, we just calculated this, Sophia. The size of a small cup, 6 kilometers across. You wanted to put the Earth into a black hole? Basically about the width of Manhattan. Run the numbers with the Earth's mass if you want to. The Earth would be, you'd be able to hold it in your hand. That would then no longer allow light to escape when you got that close. But we get bigger. This was XTEJ1650500. more suns? That is a tiny black hole. Black hole the size of Mars, how many suns does it contain? It's a meh black hole. Let's go big. Perspective, that's the size of our solar system. How many suns does this contain? Billion suns. We call these supermassive black holes. We think there's one at the center of most spiral galaxies. Called in the center of the Milky Way Sagittarius A star or Sagittarius A. Gives you an idea of how big black holes can be. Let me hit pause.